everyone. This is my pleasure to be here to present you the science with the TianQin Observatory. And I'm Yi-ming coming from Sanyang University. My today's talk will be concentrated on these 4 parts. First, I will give you a brief overview on the TianQin project. Then I'll give you some background of the TianQin science objects, together with the current progress of TianQin, followed by a summary. So we all know that the gravitational wave spectrum, just like the electromagnetic spectrum, spans orders of magnitude in frequency. And although we have made enormous progress in the ground-based detectors through the help of LIGO and Virgo and Kagra and Indigo in the future, there are still missing windows in the lower frequencies. Especially if we look at the millihertz range, we anticipate a large amount of sources, while these discoveries will return some exciting new things, new insights into the astronomy as well as fundamental physics. So these parts can only be unveiled by the spaceborne gravitational wave detections. And TianQin, the TianQin mission, is exactly such kind of spaceborne gravitational wave missions. Differ from the more famous counterpart, the LISA project, TianQin is a geocentric orbit mission, so it's orbiting around the Earth. Together with the Earth, it's orbiting around the Sun. And the arm length between the 2 satellites is about 10 to the 5th kilometers, using laser interferometry to measure the trail of gravitational wave. And this is some artistic impression of TianQin mission. So in Chinese, Tian means heaven, while Qin means hop. So TianQin is basically a hop in the heaven that awaits the cosmic plug of gravitational wave. And in order to understand the scientific objects of TianQin, we first need to understand the sensitivity curve. And as long as we can determine these 3 key components of parameters, we can decipher the sensitivity curve. The 3 key parameters are the arm length, the acceleration noise, and the positional noise. And we can straightforwardly draw this sensitivity curve. And if we overlap that with some anticipated waveforms from different sources, then we can have some idea of how many sources are we going to detect and how well can we measure in terms of parameters. And so that we enlist this compilation of different sources that we anticipate to watch, ranging from the stellar mass black hole binaries to supermassive black hole binaries. And we can use these detections to measure the expansion of the cosmos and measure the very early physical process of the universe, etc. And we need to notice that because of the solar radiation, we adopt this 3 months operation plus 3 months break operation mode, so that there will be some data gap in our data. Fortunately, if we propose this orthogonal configuration, that is having 2 sets of constellations perpendicular to each other, while both perpendicular to the ecliptics, then we will be safe from the aforementioned data gap. So we put this design into study, and we specifically want to ask how many sources can we observe. Now we have observed, in terms of electromagnetic observations, a number of, or actually 100 of the white dwarf binary systems in our galaxy. However, we know there are much more, actually in order of 10 to the 6 times more such sources in our galaxy. And we calculate these observed sources and we found out that in total we can expect to see about like a dozen of them in total. While if we're talking about all the anticipated sources, then we will be able to observe in order of like 10 to the fourth or 10,000 such sources with observation of TianQin. Also, for LISA, because it's more sensitive in the lower frequency, it will be subject to the foreground caused by the incoherent addition of all kinds of sources. And while for TianQin, because we have a slightly higher sensitivity in high frequency and lower sensitivity in low frequency, which means that we subject to lower influence of such foreground. And this plot in the bottom right shows such influence that with 5 years operation, this so-called foreground signal will be below our sensitivity curve. The result of such study is available in our paper, and you can scan the QR code for more details. And in terms of the sensitivity for parameters, we can measure the intrinsic parameters very accurately. Actually, for the frequency parameter, we can measure to the accuracy of 10 to the minus 8. If we move to more massive objects like the massive black hole binaries, then first we know that they exist, and actually such discovery have won this year's Nobel Prize. And also we have actually observed the direct imaging of the shadow of black hole. And we know that the massive black hole exists, and we know that it locates in the center of galaxies. We also know such galaxies will merge. Combining these information, we know that such black hole binaries, very massive ones, will merge. And in order to understand the evolution of the massive black holes within inside, we can use the gravitational wave detections of TianQin to understand the process of evolution and co-evolution between the massive black holes as well as the galaxy. So, however, such study so far is quite uncertain. So what we can do is to gather a number of different models and then study the performance. We gather these 5 models, the most up to, and we know for sure that they are underestimating the event rate. But the idea is that for the heavy seed models, which is the second line and the fourth and the fifth line, with TianQin observation, we can measure a significant portion of all the mergers happening in our universe. Actually, for certain models, we can measure almost every single one of them if we are assuming this TianQin 1 plus 2, the 2 orthogonal constellation configuration. And we also are interested in the idea of how well can we measure the parameters if such an event happens in very, very far away. And the bottom line is that we can measure this mass as well as luminosity distance parameters very accurately, also the sky localization ability, so that we can pinpoint the position and use this detection to decipher or distinguish the 2 different formation channels, namely the so-called light seed model or the heavy seed model. If such event instead happening in a very nearby universe, then we might even able to issue alert before the merger, actually 1 day before the merger, with an accuracy in terms of sky localization about several dozens of square degrees. So that is encouraging future that we can have this multi-messenger constraining on the merger of massive black hole binaries. If we combine a massive black hole and a stellar mass black hole, then we have this EMRI, which is extreme mass ratio inspiral, and they are hugely complicated. And this complication of waveform gives us the ability to pinpoint certain parameters like the spin, the eccentricity, etc. for this system. Again, like massive black hole binaries, we are hugely uncertain in their model. So what we do here is that we again gather a large number of different conditions and then see how many of combinations can we get. In total, we get this 12 combinations of different models, ranging in terms of EMRI merger rate from as low as 13 to as high as 20,000. Now, this uncertainty of merger rate will translate into the detection rate if we have the ability to calculate the waveform. The waveform itself is very uncertain, but we have some idea of capturing the characteristic using this so-called analytical kludge waveform, which is assuming this orbit as if there's no radiation from gravitational wave, and then using this PM approximation to derive the waveform. And eventually we can calculate the detection rate. So except for the most pessimistic model, which is M11, in this case we will detect nothing for 5 years. However, if we assume any other model, then we can have at least a number of detections, and such detection number can be as high as 400 something per year. And this work has also been published in PRD. You can feel free to scan the QR code to have more details. And this, in terms of the intrinsic parameters, we can measure these parameters very accurately to an accuracy of 10 to the minus 6 or 10 to the minus 5th, and for the extrinsic parameters, lower accuracy. And we can also look at the events that has already been detected by ground-based detectors, but the early inspiral will be detectable by TianQin. And this idea has been carried out by our group with our student Liu Shuai under the help of the great network. He has the ability to stay in UK for a while, and then we collaborate on this project. The bottom line is that we will be able to observe at least a dozen of such events with TianQin, and with better models for the for more realistic models of the mergers, we actually can aim higher number of detections, as high as several hundreds. And we can also measure the parameters very accurately, so accurate that within a typical error box of the 3D error volume, we expect to see only one galaxy within, so that we can use this information to pinpoint the gravitational wave cosmology, and such work has been undergoing. And apart from the aforementioned odd kind of events or sources, we can expect to see some stochastic background from the combination of a number of different sources. And TianQin has the ability to measure the stochastics from different sources, including the foreground, including the stellar mass black hole binaries, inspirals, and if we believe some exotic early universe process, then we can actually measure the phase transition in the early universe. And we can also use the TianQin to test general relativity, as well as testing the no-Hertzian with TianQin. Unfortunately, I'm not going to go to the details because of the limit of time. And we are also carrying out some preliminary study on data analysis. So I want to save some time for our progress. Now, TianQin has been made steady progress on the project. We have been observing this reflection of photon from the mirror on the moon, and we are working on the detection of lunar laser ranging, actually from this lunar relay satellite, the Chang'e Force relay satellite, and using the facility in our campus, and that has been on the central television show. And we have been successfully launched the TianQin-1 satellite, and the performance of that satellite has been exceeding the expectation, and that work has also been available in CQG. So again, feel free to scan the QR code. So to sum up, I'd like you to take away this information that TianQin has the ability to measure a large number of different sources, and has the ability to measure a lot of astrophysics and can decipher some fundamental physics. The final slide is some advertisement. So we are hiring with a large number of vacancies within our building. So if you are remotely related even to the spaceborne gravitational wave detection mission, please feel free to contact us if you are seeking for a job, or if you know someone seeking for a job. And thank you very much for your attention. Any questions will be welcomed.